Hi everyone. I'd like to work on one more example for the antiderivative section. In this one, we just want to, I guess, rephrase things a little bit. So here, what we're going to look at is a basic differential equation, but really everything we've looked at so far has been a basic differentiation. We just haven't really worded it that way. So a differential equation is an equation that involves derivatives of functions. And generally, our goal when we're solving those is to figure out the equation for the function whose derivative we're looking at. So these are some basic examples where I'm giving you the derivative and asking you for the function, which should sound really familiar. That's exactly what we're doing when we find an antiderivative. It can get a little more interesting and involved than this, and we'll look at that at the very end of the quarter as kind of a preview for anyone who's going to take classes on differential equations, because there's whole classes on them. Okay, the other thing that's happening here is a little shift in notation. We've been saying, okay, if you start with f, then we'll call the antiderivative big F and the derivative little f prime. That's not a rule. Here we're going to be shifting our perspective, so the function that we start with is actually going to be f prime, which means its antiderivative will be f and its derivative would be f double prime. So it's just a matter of what you're calling the function you start with. Antiderivative takes you up one, derivative takes you down one from wherever you're starting. So here we're actually calling the starting function f prime, and we're looking for f. Notice as well we're given a little bit of extra information. The point of this is we've been finding the general solution to differential equations. We've been finding the general antiderivative. This is called an initial condition when we're doing differential equations. The y-intercept will allow us to find a specific plus c and give a specific solution. So, to start off with, we just go for our antiderivative. If we want to get sine theta, we need to start with a cosine theta. The derivative of cosine theta is actually the opposite of sine, minus sine, so we need to throw an extra minus sign out in front. Then when we take the derivative, there'll be two of them, and we'll end up with the positive that we want. Okay. And then to get an e to the theta, we need to take the derivative of e to the theta, and then we need a plus c. Okay, so if I plug in, so this is my general antiderivative, so like a general solution to this differential equation, if we want to use that wording. When I plug in the 0.00, that's when I can actually find a specific solution. Cosine of 0 is 1, and e to the 0 is also 1, so it looks like we're getting c equals 0, which means our solution, our specific solution to this, what's called an initial value problem, you don't have to remember that, but that's what we'd say when we get an initial condition, is f of theta is equal to opposite of cosine theta plus e to the theta, and just that, plus 0. Okay, so here's another one where if you're feeling comfortable, you can pause and work on the next couple, and if you get stuck or want to check your answer, just come back to where we're at. So this one's really similar. This is just a little bit more practice. If we want to go up to f of t, we're going to need antiderivative. This sometimes tricks people a little bit. Again, just recognition makes this tricky, not that it's actually hard. So for starters, we want to mentally separate out that 3. So the 3 is just going to carry through to the antiderivative. 1 over 1 plus t squared is the derivative of arctan. So we're going to get an inverse tangent of t plus c. And as always, to check yourself, just try and take the derivative. So the derivative of inverse tangent, 1 over 1 plus t squared, the 3 just carries along. That looks pretty good. And then to find a specific solution, we'll say 3 pi over 4 is equal to 3 times inverse tangent of 1 plus c. There's a good little bit of trig review if we're thinking unit circle. This is telling us that tangent equals 1, so we're picturing a slope of 1. And then we're looking for the arc length, right? That's why it's arctan, because it's looking for the arc length. And it could be 2 different points, but arctangent's always going to pick the point in quadrant 1. So this right here is pi over 4, which means we have 3 pi over 4 equals 3 pi over 4 plus c. Which means that c equals 0 again. Kind of boring. I promise they won't all be 0. And our solution is f of t equals 3 times arctan t. Okay. One more, not because any of this is too crazy, but I wanted to make sure that we tackled one where we were starting with a second derivative. And notice here we're given a couple of different pieces of information, one about the first derivative and one about the original function. So we're still solving for f, right? We're still trying to find the function, which means we're going to have a couple of steps here. Oh, it's not t's, it's x's. One antiderivative is going to take us from f double prime to f prime. And the antiderivative of 6x, let's see, we better have an x squared. When we take the derivative, the 2 would drop down in front, and we get 2x squared, or I'm sorry, 2x, but we want 6x, so I'm going to multiply that by 3. 12x squared, so we're going to need an x cubed. When we take the derivative, that 3 would drop down in front, and we get 3x squared. We actually want 12, so I'm going to multiply that by 4. And then we'd have our plus c. Okay, so at this point, we're only at f prime. We still need to go to f. But we can use this piece of information, f prime of 0 equals 4, to help us find c. I want to point out, because people get messed up by this when they run into it in the homework, you don't have to have a piece of information about f prime and a piece of information about f. You could have 2 pieces of information about f. But basically what's going to happen is every time you find an antiderivative, you're going to get a new arbitrary constant. It's not the same c, so it would be a c and then a d or whatever you want to call it. And you'll need a point or some sort of information, an ordered pair for every arbitrary constant. So here, since it is f prime information, I'll go ahead and say 4 is equal to 0 plus c, which means c equals 4, and f prime is equal to 3x squared plus 4x cubed plus 4. Okay, so that's great for f prime, but our goal is to get to f. So let's take the antiderivative again. And let's say, okay, so we had an x squared, we'll want an x cubed. The derivative of that would give us 3x squared, which is perfect, so we're set. This one was made to be very nice and pretty at the end. If we have an x cubed, we'll need an x to the 4th. When we check ourselves, the derivative would bring that down to the front. We'd have 4x cubed, perfect. To get a 4, we'd have to see a 4x, and then again we're going to get an arbitrary constant. In this one, since we've already gotten rid of c as an arbitrary constant, I probably wouldn't penalize or be super worried about you using c again, but I do want to emphasize the fact that these are not the same arbitrary constant. So whatever value c takes on, in this case it's 4, that's the value of c, and d is going to potentially have some different value. And then we'll just do the same thing. We'll use our secondary piece of information. We'll say we should get -2 when we plug in 1. So 1 cubed is 1, 1 to the 4th is 1, 4 times 1 is 4. So I have -2 equal to 6 plus d, which means -8 is equal to d. And my answer is that f of x is equal to x cubed plus x to the 4th plus 4x minus 8. That one got a little crooked. Okay, so differential equations, more of the same type of work, a little bit different on the notation and getting the extra conditions. Thanks for watching.